Good morning, everyone. My name is Haiqing. I'm associate professor at University of Buffalo. On behalf of my co-authors and also former students, Dr. Lin Zhu and Marian Omidava, I'd like to share with you our work on free volume model to design high-performance polymers. And first, I'd like to briefly introduce the membranes for gas separation, and then highlight the challenge of designing high-performance polymer in an accelerated way. And most current approach is to to synthesize the polymer, measure it, and then understand it. Is there any way we could accelerate this material development process? And I also like to use an example of, excuse me, this is a high temperature hydrogen or CO2 separation. Membranes have been used for large scale gas separation, as shown here for CO2 removal from natural gas built by UOP and also by Schlumberger. And this one shows the membranes for reverse osmosis application. And also membranes has been looking at for emerging applications such as CO2 capture from flue gas. This is a pilot scale demonstration built by MTR. Excuse me. In 2019, the national academies have looked at the challenges faced by wireless separation technology. So for membrane, they identified three pillars for this technology development. Look at the process synthesis, the new compositions of materials, and also the structure property measurement. And one of the challenges here again here is to how can we perform high throughput simulation to design the high performance materials that achieve the target. And these identifications are consistent to a long-term conundrum that we have in the membrane separation field. And this has been articulated using Robinson's upper bound. It shows the selectivity as function of CO2 permeability. This is for CO2 methane separation. And this line shows that the highest selectivity possible for any possible CO2 permeability. So again, a lot of work here is we make material, we measure that, and then we try to understand that. And it's very, very difficult for us just to look at the performance, look at the targeted permeability and selectivity, and go ahead and design the polymer structure for that, and particularly for new application. So this upper bound is also described with this equation, and I'll come back to this later on. So what we like to do here is to hope to provide a way to connect polymer structure and the predictive separation property with the free volume model. Now, good thing about this free volume model is we could connect free volume to the polymer structure. So this figure shows the specific volume as function of temperature. So the fractional free volume is defined as the difference between the specific volume and occupied volume to the specific volume, right? And the good thing is that you could use group contribution method. We could treat the functional group as piece of Lego, right? So each Lego would have certain volume and also could have potentially have a certain fractional free volume. So in that way, we could actually potentially build the polymer structure based on the fractional free volume needed. And more importantly, in a classical work performed by Park and Dunpo in University of Texas at Austin, they were able to correlate the permeability as function of 1 over fractional free volume with this very simple equation. And they able to generalize this coefficient PA naught and BA value out of more than 100 polymers. And again, this just shows an example of a BA value for different gas penetrants. So once we know is the PA naught and BA value, we actually will be able to predict gas permeability and also the selectivity. And in 2015, we actually take this approach to predict the upper bound for different gas separations. And this is an example for CO2 methane. And this red line is a predicted upper bound using the free volume model. As you can see that it's actually quite consistent with Robinson's empirical upper bound. And this is the form originally developed by Benny Freeman using an activation diffusion model. And this lambda is connected to the penetrant kinetic diameter, this beta value include condensability and also the penetrant size are the parameters. And so what this tells us here is if free volume model can be used to describe the gas transport property in a quantitative way, we actually be able to express the selectivity with these parameters. There's a lambda value, there's a BA value, and PA naught value, and also the beta value, as you can see here. Now, with that equation, now we actually will be able to calculate the selectivity for various gas paths with practical industrial applications as function of 1/, fractional free volume. You can see that we can look at for CO2 methane, we can look at for uh, relative new applications such as hydrogen over oxygen separation. So once we identify selectivity, we could actually calculate the fractional free volume. We could actually take one more step. We could calculate selectivity as expressed in the red line and also the permeability in the blue line, right? So for example, if we look at CO2 methane separation, we said that we need selectivity of 40. And what that means is we're going to need the fractional free volume about 0.11 or 0.12, right? And with that fractional free volume, we could predict that, well, the CO2 permeability is very likely to be um, uh, between 0.1 and 1 if we're going to achieve that sort of selectivity. So at least it gives us some sort of order of magnitude estimate the trade-off between permeability and selectivity if we're going to design the material for this application. And this could be also useful if we look at relative new applications such as hydrogen-oxygen separation. If we say that, well, we want selectivity of 10, and we can look out and see that, well, to achieve 10, we're going to need fractional free volume about 0.08. And with that sort of fractional free volume and our hydrogen permeability is very likely to be actually less than 1, somewhere there. So I think this sort of information could be useful. It could be incorporated into the process design to show the potential of membrane separation efficiency. Just to quickly summarize, what we are looking at here is one path to along this bottom-up design, right? Once we identify the permeability and selectivity needed for membranes to be competitive with other separation technologies, we could estimate the fractional free volume needed. And then we could go back to this group contribution method that we treat each functional group as a Lego, and we could start build this polymer structure to meet this requirement of fractional free volume. And then we could design out so then we could synthesize the polymer, or we could look up literature to find the polymer structure and gas transport properties to confirm this. And once we develop this good database, we could do data mining, we could do so then we could do this high throughput computation or simulation to better design this polymer structure and also the required property. The next part is I like to take an example of this hydrogen over CO2 separation. So we've been actually looking at this application for a while. And one of the reasons is if we could have this separation, we could actually make a hydrogen with a minimized CO2 emissions. So we take a methane reforming or co-gasification, we could generate this hydrogen over CO2 mixture at high temperature. And if we have membranes that could operate at high temperature, anywhere between 150 to 300 degrees C, we could significantly improve efficiency of hydrogen purification and CO2 capture for utilization or sequestration. This left figure shows what we have at this moment. Conventional membrane polymers have very low hydrogen over CO2 selectivity. At this moment, PBI, polybenzimidazole, is a leading polymer for this application because of strong satisfying ability derived from pi-pi stacking and also this hydrogen bond. And so they have a very good hydrogen over CO2 diffusivity selectivity. And we actually trying to modify this PBI, trying to improve the performance. For example, we could cross-link this polymer PBI with a TCl. And as you can see here, increasing the cross-linking time or degree of cross-linking decrease both permeability and increase the selectivity. We also calculate the fractional free volume for this series of polymers. We also look at the cross-linking with phosphoric acid. This acid has multi protons that could have proton transfer or hydrogen bonding that could bring PBI polymer chains closer. So we look at the effect of cross-linking density or acid doping level on gas permeability. We could also calculate the fractional free volume. So we have this set of data, and we could start looking at the modeling. Can this free volume model describe this temperature effect or not? So first we look at the materials at 35 degrees C. We're able to model the cross-linked PBI with the TCl or acid dope PBI with this model for both hydrogen permeability and CO2 permeability. And as you can see here, these are the coefficients we derive. We're also able to calculate the fractional free volume at various temperatures with this simple equation. And this alpha G is the thermal expansion coefficient at glass transition at glassy state. And this temperature is at the target temperature that we want. And by fitting, we actually will be able to get this alpha G as a value of 9 times 10 to the negative 4, 1 over K. Unfortunately, we do see discrepancy of this model. The property from the manufacturer is actually 1 order of magnitude lower. So what is the consequence? Well, we'll talk about this one later on. But if we take our model value, we actually be able to describe this hydrogen permeability and also hydrogen over CO2 selectivity. We compare with the measured permeability. And if you look at it, we have a performance at 35 degrees C, 100 degrees C, 150 degrees C. And these fittings are generally actually not bad. They're actually fairly consistent. We do see some deviation for highly cross-linked polymers. Somehow our predicted value turned out to be much higher than measured value. Nevertheless, if we take this approach, we could come back and look at this application. We said, well, if we need hydrogen of CO2 selectivity of 40, what we are looking at here is we're going to need fractional free volume about 0.12. And that means that we're going to have our hydrogen permeability about less than 1. So again, this is probably going to be not too accurate. It's going to have but it should have accuracy of order of magnitude, right? But what we hope here is it could give us some general idea of predicting the gas transport properties at different temperatures. So to summarize, I hope I have shown you a path that we could connect the permeability and selectivity with the polymer structure. It's a fractional free volume model. So by treating functional group as a Lego to give us fractional free volume, we may be able to build this polymer structure based on the required permeability and selectivity. And I do want to mention here is we have some success in predicting or describing high temperature hydrogen over CO2 separation properties. Unfortunately, the fitting parameters still doesn't have a very consistent physical meaning. For example, this thermal expansion coefficient at glass state. So we still need to figure out this PA0 and BA value and fractional free volume. But I believe that if we were able to quantitatively understand these parameters, we may have a path to have a high throughput design of polymer structures for targeted permeability and selectivity. Again, I'd like to thank you for your attention. These were students who took the measurement. I'd like to thank the funding from NSF. With that, I'd like to close my